Okay, welcome to Chapter 10. We're going to leave hypothesis tests and confidence intervals behind, and we're going to look at data in a different way. We're going to look at a relationship between two sets of data. So for our first example, we're going to look at the alcohol content and the number of calories in a 12-ounce container of beer. Chapter 10 is about regression and correlation. Regression is sometimes called linear regression at this level because we're finding a line that is closest to the tendency of the data. And of course, correlation is when we say how strong that relationship is. So in Chapter 10, we're going to ask some good questions. First off, is there a relationship between two variables? The second is, what's the shape of that relationship? If that relationship is linear, then we'll be able to use our calculators to actually get a linear equation. And then we're going to ask the question, how strong is that relationship? How closely does the data lie to that line? So for our first example, we're going to look at several brands of beer and their alcohol content. So take a minute to enter the alcohol content into L1 and the number of calories into L2. You do not have to convert the percentages into decimals if you don't want to. You can leave it as 4.7, for example, for the first one. Once you've done that, let's go into our calculator and let's make a graph of this. Let's look at how this data looks. So if we put the independent data, for us, that's the amount of alcohol, into L1, and the dependent data, that is the number of calories, into L2, we can now turn on a stat plot. So we go to stat plot, and then we go into a scatter plot. So we're going to select that scatter plot icon. Then we're going to go down and make sure that L1 and L2 are selected as our lists. You can use anything you like for the mark. Whatever the default is on your calculator is fine. Now, you can graph this, but remember that we've always used zoom stat to make our graphs so that they fit and show us the data that we've got. And when you use zoom stat, you should get a graph like this one, showing the relationship on the x-axis with the amount of alcohol. So as you go to the right, you're looking at more alcoholic beverages, and as you go up, you're looking at more calories. Here's that same graph, but from a spreadsheet, and kind of exaggerated in the sense that the horizontal scale has been stretched. And you can see that out there on the left, very close to 0 in terms of the alcohol content, there is something that doesn't quite fit the rest of the data. Now, that is the O'Doul's non-alcoholic beverage. And what we're going to do is we're going to see if we can make our regression line better by ignoring data like that. But before we do that, before we talk about what we're going to do with outliers, let's talk about how we do this, what your calculator is up to when it's making a regression line. So how to do this in a very conceptual way is you start with a line that goes through the average point. And the average point is exactly what you'd think. You add up all the x values, divide by their number, you add up all the y values, and divide by their number. Now, then you have a line that goes through that, and you adjust that line. So you basically are turning it, you're changing the slope, rising it and lowering it, until you get the residuals as small as possible. So the question then is, what are residuals? Residuals are the distance between, the vertical distance between the line and the point. So let's look at an example of that. Okay, so here's what we're looking at. In blue are a bunch of data points. Remember, that's a correlation with x and y. So these blue points each represent a point in this sample space. So for our example, the horizontal axis is the amount of alcohol as a percentage, and the vertical axis is the amount of calories. So as I move these around, and notice this is entirely dynamic, I can move these around, the average moves with it. So the average is actually determined by the average of all of these blue points. So all this data determines the average. So that average is simply the sum of the x's divided by their number, comma, the sum of the y's divided by their number. Now this other point is not fixed. I can move it around. And as I do that, you can see that I'm rotating this other point through that average. The average is, we're sure that the average is on the regression line, so we're just pivoting around the average. Now, what I would like to do is make the magnitude of these residuals as small as possible. So I'm going to turn on those residuals. Notice that that's the vertical distance from the curve, or from the line. I'm not going to call it the regression line yet, because I'm pretty sure I could do a little bit better than this, but let's find out. As I move it, I can see those residuals changing. So in the top graph, there are the green vertical lines connecting the line to the point. And in the bottom graph, that's the magnitude of those residuals. And I want them to be as close to 0 as possible. Well, I want this line to be as close to the majority of the data as possible. And I don't know, I'm thinking, let's see, if I bring this up, then some are going away and some are getting closer. I see more getting further away than closer. I'm going to settle on something like that. Let's see what the real linear regression line is. I got pretty close. You can play around with this file. I'll send it out to you. But basically, we start with the average point, and then we rotate around the average point until we get the residuals as close to 0 as possible. So I've got a link in the handout that I gave you. So that link will take you to exactly that file. If you want me to send you an email with it, that would be fine too. So here's that same situation that we loaded into our calculator with the residuals shown as vertical red lines. And you can see that this linear regression line is pretty good. That's close to many of the data points perfectly, and even the ones further away from the average, it's not that far off. So the residuals are fairly small, and when the residuals are as small as you can get, the best line you can find, the line of best fit, then you have the linear regression line. We can do this in our calculator using the linear regression command. It will give us a line. A line has a slope and a y-intercept. The slope is called A in our calculator, and the y-intercept is called B in our calculator. Now, one of the strange things about TIs, and I might as well say this now if you're playing around with your calculator, there's other ways of doing linear regression. You can do it as a test, and when you do that, the A and the B in your calculator is swapped. So this is what I recommend. The moment that you use your calculator, instead of writing down A equals and B equals, because half the time A is the slope and half the time it isn't, I would immediately plug it into the formula that your calculator gives you. So when we're using the command linear regression and asking it for the line AX plus B, immediately write down what A and B's role is. So in here, AX plus B. Now, there are two variables here. There's two things running around. There's two lists in our calculator. The first list should be the independent variable. That should be taking the place of the x value. And a nice name that helps you remind yourself that it's taking the place of the x value is the explanatory variable, and you can see the x is underscored. This could also be called the predictor variable. The dependent variable, and that's the phrase that you heard in intermediate algebra, is the y variable, or the response variable. So our first axis, our horizontal axis, is the independent variable, and our y-axis, the vertical axis, is the dependent variable. And sometimes there's no distinction. You just want to see the relationship between two things. You're not claiming that one is, in some sense, causing the other. If, however, you control one variable directly, and you want to see how that indirectly affects the other, then the one you control directly is the independent variable. If time is a part of this, then time is always the independent variable. That is on the x-axis. Now, our assumptions are probably exactly what you'd think. We're going to do things a tiny bit differently from the text, and I will point that out. And as we go through these, I will show you that. And the reason for that is because we're trying to make these assumptions fit what our calculator does. And at times, our calculator is great, and there's some other things that our calculator doesn't do all that well. Now, I'm showing you exactly what Kate does in the text. She says that the set xy of ordered pairs is a random sample of the population of all such possible pairs. And that's a kind of interesting statement, and your first response to it probably is, well, yeah, we need a random sample. So clearly that would be something to highlight from this sentence. But you might ask yourself why she's using the ordered pair notation, x, y. And that's actually very important. She's using that notation because she's reminding you that data comes in pairs. In other words, for our example, the alcohol content and the calorie content isn't just randomly selected and thrown together. It's the calorie and the alcohol content for a particular beer. And then another ordered pair is that same pair of data for a different beer. So she's using this notation to remind you that whatever you choose, whenever you choose one variable, make sure you're getting the other variable for that same sample. Now, one of the things that is somewhat difficult for us is that we need to have a normal distribution. That shouldn't surprise you. But it's a little bit more difficult to do than in previous sections. So we're going to do this in two ways. We're not going to do one of the ways that is probably best, and then we're going to add a new way. So first off, the first thing we did with that data was we plotted it. Did it look like it lies on a line? We imagined trying to fit a line around the average, and you can play with that file that there's a link to, and I'll send you as well. Now, that is a good way to see if this is a good idea, if linear regression works, is just to look and see. I mean, really, honestly, we're talking about looking at the scatter diagram and seeing if it has a linear distribution, if it kind of already lies along a line. So I'm going to ask you to do that. Remember, you have to enter the data every time anyway, so you might as well take a look at it. It's also a good way to check that you've entered the data reasonably correctly. Now, the next thing that I'm going to talk about is something we're going to do because it's easy for the calculator to do, and because it makes our answer that much closer to accurate. This is not in the text. This is a step that we're adding, and that is to eliminate outliers. So we're going to remove any points that appear to be outliers. So what does that mean? That's not difficult with our calculator because our calculator actually has a feature, and that is that special box and whisker plot with outliers. So we're going to go into StatPlot, we're going to make a box and whisker plot with outliers, and we're going to see if we have any outliers. So you have to make sure, just to summarize, that first assumption requires that you've got data in pairs. So for each x and each y, those actually came to you together. You didn't randomly shuffle them. And that was a random sample. You didn't simply select, in our example, beers with very high alcohol content or beers with low alcohol content, or anything that wasn't random. And then the second thing that we decided is that showing that our data is normally distributed with our calculator is a little bit difficult. So we're going to do two things. The first thing that we're going to do is we're going to actually look at that data to see if it has a linear pattern. The second thing that we're going to do is we're going to remove any outliers. So we're going to use a box and whisker plot to find them. and then we'll have to edit and go into the lists and delete them. What we're not going to be doing is to look at the residuals. It would be great if our calculator could create a table of residuals for us easily. In fact, I'm considering writing a program to do that, but for now, I think our 2 steps are good. Now you might say, are we really doing anything useful? Is this actually helping us? Is this taking us in the right direction? Are we just creating a line and who knows whether it is of any use to us? So I want to foreshadow that. There is a linear correlation coefficient, we're going to call that R, coming, and that's going to tell us the strength of that relationship. In other words, how well the line really represents the data. Okay, so we've already looked at a scatter diagram for the data. You can do it again. You've got the data in memory. Now we're going to go in and look at a box and whisker plot with outliers, and we're going to see if there are any outliers. So we're going to go into plot. We're going to select that first box and whisker plot icon. That's the one with the other 2 little dots. Those 2 little dots are when it's using the 1.5 standard deviation rule to find outliers. So when we do that, we're also doing this only for one of the sets of data, which is assuming that we've done a good job finding the independent versus dependent variable. So just one set of data, and we look at our box and whisker plot, and almost immediately we see that there is an outlier. And you might remember that when we plotted this and we stretched that horizontal scale, it was fairly easy to see that that non-alcoholic beer was an outlier. So we're going to go in and delete it. So that actually means going in and editing those 2 lists. Don't just delete it from one list and not the other. Delete the same data point, that is the same information from both. We're then going to go back in and make a scatter plot just to make sure that it's gone. And notice that the picture should be clustered around the remaining data if you use zoom stat. Now, when we use linear regression commands in our calculator, we need to have the diagnostics turned on. Now, you don't have to do this but once, but if you've got a new calculator, you may have to do it. So make sure your diagnostics are turned on so that you get good information and the same information that I'm going to get on the screen when I run these linear regression command. So in our TI, we go to stat and then calculate and then linear regression. We've got, we also have the way of storing plots, so we'll talk about that as well. So when we go in to the linear regression command, it's going to ask us for 2 lists. So here's L1 and L2, and it's going to ask us if we want to store the linear regression equation, which is a really cool feature because we can then look at it. We don't have to just recopy it off the screen. You can keep it. Now to do that, where it's asking you, do you want to store the linear regression equation? I chose to store it in equation in y sub 1. Now to get y sub 1, and this is while you're on this screen and while that question is highlighted, you can go to variables, then select y variables, then select functions, and the first one will be y1. If you want to use a different y, you can just scroll down to another one. But that keeps it so that you can return to it, which is a nice feature. When you press calculate, you get, if your diagnostics are turned on, exactly what I've got. Now there is our A and our B, but don't write A and B down. I really recommend that you write it in the context of the equation. So where you see that A, just write that in place of the slope. Where you see B, write that in place of the y-intercept. Now there are the r's that I foreshadowed on the previous page, r and r squared, and that gives us a sense of how useful this is. We'll talk about that in sections that are coming up. Now if you go into your plots, not your stat plots, but your plots, you can see that y sub 1 has been loaded with this linear regression line. Now, what's amazing is we can now graph this. So if you press graph, and remember you've already done the scatter diagram, so you've got that data and it zoomed. You probably used zoom stat so that you got a nice picture with that data on the screen. So when you now plot this line as well, you can see not only the data in those little squares, but also the linear regression line, which is just beautiful. It shows you that you can check this kind of just by looking. So what does this mean? So this means that we have a slope, and the slope is the thing that's being multiplied by x, right? That's the mx plus b. The b is the intercept, the y-intercept. So this is written in the familiar form. You may have to scroll over to see the x and the b, but you can find this in your calculator. Notice that I rounded to 1 decimal place, and it comes out to us in mx plus b format. And I'm going to say again, and this is just a reminder that when your calculator gives you a and b, I really recommend that you write that information down as you need it and not as a and b. Put it in the equation, because when we do hypothesis tests for the linear regression lines, the roles of a and b are swapped. So as soon as you've got an a and a b, use it right then. Okay, so we're going to work through a linear regression question for our beer example. It says to use a random sample. Well, that's nice. We're told that this beer was selected by random methods of different beers' alcohol content and calories to find the linear regression model for the alcohol content and the number of calories. And remember that these were all 12-ounce containers of beer. So the first thing we do is state our random variables. There's 2. We've decided that the independent variable should be the alcohol content. So that's going to be our x value on the horizontal axis. And then on the y value is the number of calories of that particular beer. The first thing we need to check is that it was a random sample, and we were helpfully told that in fact it was a random sample. And now we need to make claims about it being normally distributed. Now I'm going to say that it appears to be normally distributed because of what follows. So let's take a look at that. When we graphed the scatter diagram, it certainly looked as though it was linear. And we've done one thing more. We found an outlier and we deleted it. So the outliers have been deleted. And for those 2 reasons, one just by looking and one by deleting the outliers, we can assume that the data is normally distributed. Now the regression line, we've seen that in the calculator. So out it comes and we write our answer. Now, once we have a linear regression line, we actually have a fairly powerful tool. It helps us make predictions about where a beer that we hadn't encountered before would lie on this line. So here's a question. It says to use the regression equation, that's the one in your calculator, you've stored it in y sub 1, to find the number of calories in a beer with the alcohol content is 6.5%. So you're assuming that this beer behaves like the others, has the same relationship between calories and the alcohol content. So you can do this the old-fashioned way. You can say, well, that's the alcohol content, that's our x value. So you can simply plug that alcohol content into our linear regression equation for our x value. And when you do that, you've got an arithmetic problem. So you set up the multiplication, you do the addition, and then you state your answers. We'd expect a beer with 6.5% alcohol to have 196 calories. You can do this in your calculator in a very nice and very elegant way. You can use function notation. So remember how you can use vars to go grab that y sub 1. So if you're on the home screen, you can grab y sub 1, you can open parentheses, you can put in what you want for x, and then you can press enter, and it'll do all that work for you. It'll plug 6.5 into the function called y sub 1. Now what does this mean? This means that if there's a beer out there that has 6.5% alcohol, then it's probably got about 196 calories. So we're making a prediction. Now, let's compare that to the other way that we have of using a set of data to make a prediction about a new piece of information. The mean number of calories for the beers in our sample was 170 calories. Now, 170 is a lot less than 196, but that's because, or perhaps because, that may be correlated to the fact that some of these beers in our sample had an alcohol content less than 6.5. And we noticed very clearly that as the alcohol content increased, so did the number of calories. So it would definitely seem like 196 calories is a better estimate than using the mean. So that's pretty good. So we're actually going to say that the regression equation, so regression, linear regression, taking the same place, is a better estimate of the number of calories of any data that we can show is normally distributed and was chosen at random than the mean. So we've already used our linear regression equation to do something better than the mean was able to do. Now this is called interpolation, and the emphasis here, to my way of thinking, is on the inter part. This is a question about a beer that we haven't encountered. It's not part of our sample. But 6.5 is well within the alcohol levels of the beer in our sample. So it's about what we would expect from another randomly selected beer in our sample. Interpolation means that we're asking for something in the region of the sample itself. Now compare that to extrapolation. And here I see an emphasis on the word extra. I'm thinking of it as outside of the realm of our samples. So we're going to do another example, and the arithmetic will be the same. But because 2% alcohol is outside the range of the data that we collected when we were looking at our sample, we're going to have to say this in a different way. In fact, the moment that you look at this, you might think to yourself, that's interesting. I'm not quite sure that that's right. So let's begin by doing the arithmetic. You've got the equation for the linear regression line. We're asked to find what the number of calories in a 2% beer would be. So we plug 2% into our equation, taking the place of x, because that's our x value is the percentage of alcohol. We do the arithmetic, and we discover that this beer should have 78 calories in it. Well, that's already looking a little bit fishy. Now, remind yourself that you can do this with your calculator from the home screen. You can just find y sub 1 from the variables, and then use the parentheses to make function notation and plug in that too. You'll get 78. Now this says that a beer that's 2% alcohol content has 78 calories. This doesn't seem like a good estimate. And this estimate is what's called extrapolation. Extrapolation is when we're trying to predict values outside, and I guess you can say far outside, the range of the original data. And of course the original data is our sample. We were trying to do everything within our power to make sure that our sample was random and normal. So something outside of our sample gives us pause for thought. So we can never really be sure that the regression equation is valid for data outside of our sample. Now, what does this mean? What does the parts of our linear regression equation mean? Well, let's first talk about the slope. The slope is a rate of change, and that's exactly what you'd hear said in an algebra class. It's the rate of change of the dependent variable compared to the independent variable. So, in other words, how one changes, how the dependent variable changes, how does that change the independent variable? In this case, the slope, that coefficient 26.3, is the number of calories you expect to add every time you add 1% to the beer content. So the beer content goes up by 1%, you expect 26.3 more calories. There's also the Y-intercept, that 25.0. The intercept is what you'd expect if the Y variable is, or for the Y variable, if X is 0. In other words, a beer with 0% alcohol. Now, that might be stretching the definition of the word beer. That sounds more like water or fruit juice to me, or a soda. So we really can't predict something that is not among what we're talking about in our sample. So it's not really meaningful. We can interpret the slope as the increase in the dependent variable as the independent variable increases by 1, but the intercept is not all that meaningful to us. It's almost certainly outside the range of our samples. Now, here's an example from our book that I think is interesting in itself, because it's referring to what happens when you extrapolate. So, the dangers of extrapolation. When you use linear regression to come up with an equation, we can predict the growth of a city. So, Flagstaff, Arizona ran into these problems. So, it was using extrapolation to determine how fast and what its population would end up at. So, in 1995, the population of Flagstaff would be well over 50,000. But when the census for 1995 actually happened, the population was less than 50,000. And the reason that that estimate was so far off is because they had extrapolated the growth factor from the early 1990s. And of course, it had changed since then. And growth factors can change for many reasons: employment, stagnation, growth, disease, being written up in national magazines as a great place to live. All of this makes us remember that extrapolation can predict a value, but it may not be anywhere close to where we end up. Okay, one more example. We're going to look at skeletal remains. So we're going to correlate the length of the metacarpal with a person's height. So the height of a person in centimeters and the length of their metacarpal in millimeters were collected. So first create a scatter plot and find a regression equation between the height of a person and the length of their metacarpal. Then use the regression equation to find the height of a person with a metacarpal of 44 millimeters and a metacarpal of 55 millimeters. Which height that you calculated do you think is closer to the true height of that person, and why? So first we're going to work through this. We're going to load this data into our calculator, maybe L3 and L4. Our random variables, we're assuming that the length of the metacarpal is the independent variable, and that affects the height of the person. Our assumptions were that this sample is random, but golly gosh, we are not told that it's random. So we don't know that this sample is random. The second thing we want to show is that it is normally distributed. We're going to use the scatter diagram, and we're going to use the box and whisker plot with outliers to determine that. And when we do those two things, we learn that, yep, it looks pretty linear, and there were no outliers. So we're going to compute the linear regression line. So there it is. That's what I got out of my calculator. Now you're going to plug x into this, and we've got two different x's. You're going to plug 44 into this, and you're going to see what you get for the height. So, and remember the units. 44 is millimeters, the height is centimeters. The 44 is well within our sample. So notice that we've got 47s at the bottom, we've got 45s, so well within this region. So when you use linear regression to estimate the height of someone whose metacarpal is 44 millimeters, I would call that interpolation because it's inside the data that you've got. The same cannot be said for the second question. If we're now asked about someone whose metacarpal is 55 millimeters, well, that's no longer inside of this data. That's well outside. I see a 49, I see a 51, but 55 millimeters is outside the range of that data. So when we use the linear regression formula to find the height or the expected height, this one's going to be extrapolation. So when it asks us which one we think is closer to the true height of that person, we'd have to say that the one that we found through interpolation is the better of the two. So we would guess that the estimate that we made for the 44 millimeter long metacarpal is the better of the two, closer to the true height.